Okay, let's take a look at the trapezoid rule. And before you watch this video, I would suggest watching the midpoint rule video first, and it'll make some of this stuff make a little bit more sense. So the only difference between the midpoint rule and what we're going to do here is that rather than using rectangles, we're going to use trapezoids, and that has certain advantages that you'll see here in just a second. Now, we'll use a fairly simple curve, y, or f of x is equal to x squared for our demonstration, and we'll begin by dividing this interval. We've got a closed interval from A to B, and we'll divide it up into 4 equal size intervals. So in that case, n will be equal to 4. So we've got 4 equal size intervals, and here they are right here. Now, just to give them some numbers, we're going to go from A to B, and if we divide up into equal parts, each one of these would be delta x. So we'll just call this one, just to give it a number, we'll call it x1, call this one x2, and call this one x3. And each one of these has a width, and that width is delta x. And this one would be delta x, and delta x, so 4 equal widths. Now, we've done this before, where delta x would be equal to, in the same formula that we've used in the past, again, is just b minus a, the width of the interval divided by the number of intervals. So in that case, it would be b minus a divided by n. So that will give you the width of each one of these intervals. Now, the first difference is that rather than using rectangles, we're going to use trapezoids. So we'll come into each one of these and we'll put trapezoids in here. And it's going to wind up looking like this. So I'll go from here, and here, and here, and here. Now, to get a trapezoid, what that's going to be is a straight line from each one. So what a trapezoid is, 2 sides are parallel and 2 sides are not. So if I drew a straight line from here to here, we'll go from here to here. If I draw a straight line, it'll be that green line right there. Then if I went up to here, I'd have another one. Then I'll go from here to here. And finally, now this thing looks like a triangle. What it actually is a trapezoid in which the left edge has a height of 0. But we can still consider it to be a trapezoid. So I'll go from here to right here. Okay, now what I've got there are 4 trapezoids, and I want to find the sum of the area of those 4 trapezoids. Now, just a reminder, what each one of these are going to be. This one, let's take a look at the height of each one of these. So the height of this trapezoid right here, this side, would be f at, try that one more time. This side right in here, from here to here, this is going to be f evaluated at b. The height of this side right here would be f evaluated at x sub 3. The height of this side would be f evaluated at x sub 2. And finally, let's go down to here. The height of this side would be f at x sub 1. And finally, this last height, which in this case has a height of 0, would be f at a. So that's going to be the height of each side of those trapezoids. Now, first of all, just a reminder what the formula is for the area of a trapezoid. It's the width of the trapezoid divided by the average of the heights. So for an individual trapezoid, it will look like this. The area of a single trapezoid would be the width of the trapezoid times the 2 height, we'll call it height 1, plus height 2 divided by 2. So if you average the 2 heights and multiply times the width, you'll have the area of a single trapezoid. Now, in terms of our picture, here's what it's going to look like. The area of the 4 trapezoids that we have looks like this. So the area would be Now, the width of them is delta x, which in this case would be b minus a. And since they all have the same width, we can do this. We can factor it out as, you can think of it as being width 1 times the average of the heights 1 plus width 2 plus the width 3 plus the width 4. Then the average of the heights goes here, 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 and here. Now since they all have the same width, you can factor that width out. So we can make the width be b minus a, so you'll start by having a b minus a right here, divided by n. Then each one of these are going to be, now it's just a matter of adding the heights together and dividing by 2. So let's look at this first trapezoid. It's going to be the average of this, so you'll have f at a plus f at x1 divided by 2. That's the first trapezoid. Then plus, now this trapezoid, f at x1 plus f at x2 divided by 2. That'll be that one. Now look at the third trapezoid. It's x2 and x3. So this will be plus f at x2 plus f at x3, that average height. Then finally, for the last trapezoid, you'd have f at x3 plus f at b. So f at x3 plus f at b. And that average height divided by 2. Okay, the next thing you do is this. Since all of these are divided by 2, you can go ahead and bring a 2 to the outside. So what we'll do is, you've got each one of these things is divided by 2. So you can take this 2, all of these 2's, and we'll move it to the outside and put it right in there, which will get you to this. That means that the area would be, now it's going to be b minus a divided by 2n rather than n. And all that does is now everything in here is no longer divided by 2. So you'll have f at a plus f at x1 plus f at x1 plus f at x2 plus f at x2 plus f at x3 plus f at x3 plus f at b. So when you factor out the 2, this is what's left over. Now look at what's left inside this thing. What you've actually got, you've got an f of a all by itself. But notice, you've got f at x1 twice. You've got f at x2 twice. You've got f at x3 twice. So all the ones in the middle occur twice. The left one, the left endpoint and the right endpoint just show up once. But everything else is twice. So what that does, it gets you to this. The area would be, first of all, here is b minus a divided by twice n. And now you can do the following. First of all, put the f of a all by itself. So you've got f at a. But now put these two together. What that's going to give you would be, and I think I'll do it with a red in front of it, this is going to be twice f at x1. Plus, then again, you'll have twice f at x2. So you've got a 2 here. So twice f at x2. Then plus, and again, twice f at x3. So we'll put those 2's in red just so they kind of stand out. So this is going to be f at x3. And then finally, the last one is just all by itself. So f at b. And what this gives you, this is the formula for finding the area under a function using the trapezoid rule. So it will be that right there. And just remember, the first one and the last one just occur once, but you double all the ones in the middle because the side shows up twice. So that's where the formula comes from. So now with that in mind, let's go back and take a look at the original problem again. So we'll move it up and we'll actually solve the problem. So let's turn all this stuff off. And starting with what we've got here, let's take a look at these trapezoids. So again, my trapezoids, I think I'll draw them one more time in green here. This one goes up to here. So there, 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 and there. And then the trapezoid itself actually is a line that goes like this. And then like this. And then like this, and so on. Now before we get started, just to remind you, this is not going to be an exact answer because of the following. What will happen is, in this particular problem, notice that the final area is actually going to be a little bit bigger than the actual area because I have not accounted for this little area in here, this little area in here, and so on. A little bit of an area in here. So I'm going to get a pretty accurate answer, but it won't be exact because of those little red areas. So my answer will actually wind up being just a little bit too big. Okay, now with that in mind, let's go ahead and put the trapezoid formula back on here again where we can look at it. So here's the formula, and remember all the middle ones are doubled. So in general, it would look like this. And you get to pick as many intervals as you'd like to. So in this case, we're picking n is equal to 4. Now, for a specific problem to work with, let's go ahead and do this. We are going to find the area under x squared in the interval from 0 to 2. So on our particular problem, I think I'll put them in red here. I'm going to go from a is equal to 0, b is equal to 2. Now, if we divide these up into 4 equal size intervals, and again, use your little formula, you can find out let's find the width of each one. So delta x would be equal to b minus a divided by n. So in our problem, we're going to have 2 minus 0 divided by 4, which would be 1/2, and that is going to be the width of each interval. So I want to write those on there. So if each one of these is 1/2 and it goes from 0 to 2, this point would be 1, this point would be 1/2, and this point would be 3/2. So go ahead and put the points that you know on there. Okay, now when you solve the problem, it's just a matter of putting the values into this formula. So what we'll do is this. It's going to be, the area is going to be equal to, in parentheses, now again, b is equal to 2, and a is equal to 0. So you can see it up here also. So a is equal to 0, b is equal to 2. So this is going to be 2 minus 0 divided by 2, and in our problem, n is equal to 4. So this is going to be 4 right here. And then put parentheses around that. Then what you do is the following. You're going to evaluate the function at a, then the function at x1, and so on. So what we'll do is, what the first thing says is this. Plug the value of a into the function, which is x squared. So you'll take, we'll just go ahead and put it like this. This will be the function evaluated at 0. Actually, I think I'll do that in red so they kind of stand out a little bit. So let's say we'll plug a 0 into the function. Then plus twice the function evaluated at x1, which is 1/2. So we'll plug a 1/2 into there. Then plus twice the function evaluated at x2. and x2 is a 1, so we'll plug a 1 into that. Then plus twice the function evaluated at x3, which is 3/2. So this is going to be twice the function evaluated at x3, which would be 3/2. And then finally, plus the function evaluated at b, which is 2. So this would be plus the function evaluated at b. And we'll put that in as a 2. Okay, so it actually looks like that. We'll go ahead and make this one black just so it looks like all the other ones. Put it in brackets. Well, now it's just a matter of evaluating this thing. So let's go ahead and see what we've got here. We'll move it down a little bit where we can see it. What this will give you would be basically 2/8, which would be 1/4. So this will turn into 1/4 of. Now for these, just take the 0, and again, take the 0 and plug it into x squared up here. So that's going to give you, put a 0 into x squared, and you'd have 0 squared. Then you've got plus twice. Now plug a 1/2 into x squared. So this would be 1/2 squared plus twice, plug a 1 into x squared, plus twice, plug a 3/2 into x squared, and then finally, plus just plug a 2 into x squared, which would give you 2 squared. So take each point and plug it into x squared. So what that's going to give you would be 1/4 of. Now when you take 0 and square it, you'd have 0 plus twice. Now when you square 1/2, you would get 1/4 plus twice square the 1, you'd get a 1 plus twice square the 3/2, square the top, square the bottom, you get a 9/4. And then finally, plus square the 2, and you'd get a 4. So you're down to that. Okay, now the next thing would be to simplify this. So what this is going to be equal to would be 1/4 of, and you've got the 0. 2/4 is the same thing as 1/2 plus the 2 plus twice 9/4 would be 9/2, and then finally plus 4. Now I'll go ahead and put the whole thing over halves, so this is going to be 1/4 of 1/2 plus 4/2 plus 9/2 plus 8/2. So what that would be equal to would be 1/4 of, and if you add all these together, 10, 8, and 4 would be 22/2, which would be 1/4 of 11. So the final answer is going to be 11/4. And what this is going to be, that's going to be the approximate area. So we'll call it the approximate area using 4 trapezoids. So with that in mind, let's kind of back up and look at the whole problem again. So again, starting from the beginning, divided up into 4 equal intervals. And here's the key point right here. You've got to find the x value that you're going to evaluate the sides at. So you've got 0, 1/2, 1, 3/2, and 2. And this tells you what numbers to plug in here. So you'll plug in 0, 1/2, 1, and so on. And then from there on out, it's just a matter of plugging in the numbers and running through the algebra. And just a reminder, the first number and the first side and the last side are not multiplied by 2, but all the points in the middle are multiplied by 2. So an easy mistake to make, don't forget to put twice here, and twice here. So all the ones in the middle are multiplied times 2. And then just run through the algebra, and when you finally get finished, this will be the approximate area using 4 trapezoids. Now it'll actually be, for this problem, it'll actually be a little bit bigger than what the actual area is. But as you can tell, looking at the picture, all you haven't accounted for is that little red area in between the straight line and the curve, so it's going to be fairly accurate. So that's a sample using the trapezoid rule.